We're ready to get into Math Assignment 11, video number 11. This is going to be a review for the wastewater side of the industry. Video number 12 will be the water side of the industry. So you can take one or both. It's up to you. Why not do both? Why not get the practice in? Repetition is the key here with the water wastewater math. It's what works for me. Repetition, teaching it to somebody else. I highly encourage you all, especially if you struggle with math the way I do, take aside one of your coworkers, one other operator, sit down with them, help them understand it, teach them how to do the math. You use a different part of your brain when you have to explain it or teach it to somebody else and help them understand. So there are 33 questions, I believe. 33 questions. This is going to be a long video, but you'll be surprised, I think, by how quickly we can move through it. And once you do this on your own, it will take even less time. There's a few questions in here that weren't covered in any of the videos, and you'll see why. Once you've gone through all the videos, you should have enough information to figure a few things out, to be able to look at a question that you might not have been directly asked in this program when you take your certification exam. But I've given you enough information that you should be able to look at it, break it down, and say, all right, I know how to do this. So let's go ahead and get started. Question 1. The first several questions is going to cover the same theoretical wastewater treatment plant. So let's get started. A treatment plant is equipped with an aeration basin 94 feet in length and 62 feet in width. The depth of the upstream side of the basin is 12 feet. On the downstream side, the depth is 15 feet. The flow through the plant is 0.825 mgd. The water in the basin has been treated with 31.65 pounds per day of magnesium hydroxide to raise the pH. The effluent feed is 35.78 pounds per day of chlorine for disinfection. After an hour of contact time, the free chlorine residual is 2 milligrams per liter. The treated effluent is then dechlorinated with sulfur dioxide at a rate of 0.5 milligrams per liter more than the free chlorine residual. Okay, first several questions, it's all going to be the same scenario. Question number 1, what is the surface area of the aeration basin? So we want to know what the surface area, we want to calculate the surface area. For surface area, we are going to need area will be expressed in square feet. And we know that area is equal to the length in feet multiplied by the width in feet. So let's use that formula and plug in the information we need. We have the length of the aeration basin, which is, and I'm going to reread this to myself as I go along. I want to make sure I'm grabbing the right information. So, for instance, the plant is equipped with an aeration basin 94 feet in length. Okay, there's my length, 94 feet. Now I want the width. If I don't read the question, I might just go ahead and grab the depth of 15 feet. If I multiply 94 by 15, I'm going to get the wrong answer. Guaranteed, if I multiply 94 times 15, the answer will probably be one of the choices, and it'll be the wrong choice. So let's go to 94 feet in length and 62 feet in width. $62 All right. I have nothing to cross cancel here because I have feet, and that matches up with the unit of measure that I want for an answer. 94 multiplied by 62 equals 5,828 square feet. The answer is C. All right, question number 2. Same scenario. Calculate the volume of the basin in cubic feet. So we want volume, and it will be in cubic feet. Now we know it's a rectangular basin. It has a length, a width, and a depth. There's also a depth here. So this is going to get interesting. Calculate the volume of the basin in cubic feet. So let's start with the length in feet, the width in feet, and the depth in feet. 1, 2, 3 cubic feet. Okay, I know I'm on the right track here. Here's the thing. A treatment plant is equipped with an aeration basin 94 feet in length and 62 feet in width. The depth at the upstream side of the basin is 12 feet. On the downstream side, the depth is 15 feet. So the bottom of this basin is sloped from 12 feet to 15 feet. 12 feet on the upstream side, 15 feet on the downstream side. That means that any solids that settle out at the bottom of the basin will work their way, they'll slide their way down to the downstream side, which is what we want in a wastewater plant. So, so what we're going to do is, I'm going to title this one Upstream. And I'm going to show you why here in a moment. So we have a length of 94 feet. Aeration basin 94 feet in length. 94 feet. We'll do the width. The width is 62 feet. Now the depth on the upstream side of the basin is 12 feet. Hang with me here, this is going to make sense. Kind of covered this before. We're going to cover it again. So we have feet here, feet here, feet here, cubic feet. That all matches up. Now we can make our calculation. 94 feet times 62 times 12. And that's going to give us 69,936 cubic feet. Now we have the upstream side. What is the downstream side? So let's go with volume in cubic feet downstream equals length in feet times the width in feet times the depth in feet. That's the formula we're going to use. We have 1, 2, 3 cubic feet. So let's add in the information we need. Now we know that its length is 94 feet. The width, excuse me, 62 feet. And the depth on the downstream side is 15 feet. Let's check this out here. We got feet, feet, feet. Looking for cubic feet. Now we can make our calculations. 94 feet times 62 feet times 15 feet, and that's going to give us 87,420 cubic feet. Now what did we do? Well, this is a sloped bottom. We want to do an average of these two volumes in cubic feet. So I'm going to take 69,936 cubic feet. I'm going to add it with 87,420 cubic feet. I already have this on here, but let's go ahead and zero it out. 69,936 plus 87,420. That gives me 157,356 cubic feet. Am I done? Nope, I am not done. I want an average. So let's get this 157,356, divide that by 2. Divide by 2, and that's going to give me 78,678 cubic feet. What's the best answer? The best answer is G. Before we go on to question number 2, before we go on to question number 3, let's look at question number 2. We calculated the volume in cubic feet for the basin. We had to average it. So, question number 3 asks a very good question. How much water is in the basin? Well, we know that once we've calculated the volume in cubic feet, we can multiply that by 7.48 gallons per cubic foot. Excuse me. That's going to give us the volume of the basin in gallons. This is one of our conversion factors found in the ABC formula conversion tables, the math formula sheet. So let's write that down in an equation. I want volume in gallons, and that equals volume in cubic feet multiplied by our conversion factor, 7.48 gallons per cubic foot. Let's rewrite this formula so it makes sense. Well, with the factors that we already know. So we already know that the volume is, put that away already. From question number 2, we know the volume is 78,678 cubic feet over 1. And we have our conversion factor, 7.48 gallons per cubic foot. Can we cross cancel? We sure can. We have cubic feet over 1. We have cubic feet beneath the dividing line under gallons. I can cross cancel these out. That's going to leave me with gallon and 1, which gallon times 1 is gallon. That matches up with the unit of measure we want. So 78,678 times 7.48 gallons per cubic foot is going to give us 588,511.44 gallons. What's the best answer? The best answer is K, 588,000 gallons. All right, let's go to question number 4. Same scenario. Question number 4, calculate the dose in milligrams per liter of magnesium hydroxide. Well, we have magnesium hydroxide, and it's being used to raise the pH. Let's just highlight this entire section. Okay, we'll just do it like that. So we have a feed problem. If you go to the back of the formula conversion table, the ABC math formula sheets, you're going to see the Davidson pie wheels. It's a circle with pieces of a pie. I make it easy. Just draw it out like this. Now each section has a meaning. This is a feed problem. Feed is in pounds per day. The flow is in million gallons per day. The dose is in milligrams per liter, and our final piece of the pie, 8.34 pounds per gallon. Water weighs 8.34 pounds per gallon. So calculate the dose in milligrams per liter of magnesium hydroxide. Magnesium hydroxide is used to raise the pH from acidic to more alkaline or more neutral. Neutral is the best. We'll go into that in later videos that will be coming here in the next few months. So the water in the basin has been treated with 31.65 pounds per day of magnesium hydroxide to raise the pH. So we know it's 31.65 pounds per day. What is the flow through the plant? Well, the flow through the plant is 0.825 million gallons per day. So we want to determine what the dose is. The dose is going to be, to do the dose, to calculate out the dose, we want to multiply the flow. We want to multiply the flow times the dose times 8.34 pounds per gallon. 0.825 times 8.34. That gave us, because we have dose is our x. That's our unknown. We multiply 0.825 by 8.34, and that will give us 6.88. Our feed, 31.65 pounds per day. So let's take that 31.65 And this line right here represents division. This is our division line. Divide that by 6.88, and we get 4.600. Our dose is 4.66 milligrams per liter. That is our piece of the pie. The best answer, 4.7 N. Question 5, same scenario. Very similar question to question 4, except this time we want to calculate the dose of the chlorine used for disinfection. Well, we know at the effluent side, at the disinfection side of the plant, the feed is 35.78 pounds per day of chlorine. So again, let's draw out our pie. We have feed in pounds per day. We have flow in million gallons per day. Dose in milligrams per liter, and our weight of water, 8.34 pounds per gallon. So we have our feed. Our feed is 35.78 pounds per day. Our flow, the flow through the plant is 0.825 million gallons per day. So again, we're going to have to, we can go ahead and write the feed down right here, 35.78. Now let's do some multiplication. Our flow, 0.825 multiplied by 8.34, that gives me 6.88. 35.78 divided by 6.88, and that gives me 5.2 milligrams per liter. The correct answer is M. Question number 6. What is the chlorine demand? Well, chlorine demand equals the chlorine dose minus the chlorine residual. That's our formula. When the water goes into the disinfection side, or the disinfection treatment, we dose it with chlorine. At the end of that process, or during that process, chlorine attacks everything in the water that it wants to react with. Chlorine will react with practically everything except H2O, hydrogen and oxygen, which makes up water. So the chlorine is attacking bacteria and other microorganisms, including plants like algae. It's attacking dissolved gases and dissolved metals or dissolved minerals. It's attacking that, and as the chlorine attacks it, the chlorine is getting used up. So if I have a bacteria and I have chlorine, the chlorine's going to attack it. It might take a bunch of chlorine to attack that bacteria and neutralize it or kill it or destroy it. But it's going to attack it until there's no more chlorine or until the bacteria has been destroyed, devastated, killed, inactivated, however we want to put it. So we want to determine what the demand is. We're going to do that. Let's look at, we have the dose, residual. So the free chlorine residual is 2 milligrams per liter after an hour of contact time. Hour is pretty typical. So let's keep that in mind. So we know from question 5, the dose is chlorine dose is 5.2 milligrams per liter. We're going to subtract the chlorine residual. This is the chlorine that's left over after an hour of contact time when we hope the water has been adequately disinfected. Since we have a chlorine residual of 2 milligrams per liter after an hour, we can feel reasonably sure that because that residual is there, the chlorine has reacted with everything in the water it wants to react with, leaving free chlorine. It leaves a residual amount of chlorine, which is less than the dose. So we know the dose is 5.2 milligrams per liter. We're going to subtract the residual, and that's going to give us 3.2 milligrams per liter. That's our demand. Dose minus the residual equals the demand. How much chlorine it took to disinfect the water. The answer is S. Question number 7. What is the pressure in PSI reading on the pressure gauge at the downstream side of the basin? Well, the downstream side of the basin, that's my work phone telling me that work is still continuing at the end of the day. On the downstream side of the basin, the depth is 15 feet. So what is the pressure? I have a contractor working at one of my lift stations on the generator, and he's letting us know, and my lead operator is responding to him, what needed to be done. All right. So what is the pressure in PSI on the pressure gauge at the downstream side of the basin? PSI equals the downstream side of the basin is 15 feet in depth. So we're going to take depth in feet and we're going to multiply it by a constant that we know, or conversion factor, excuse me. It's a constant, it's a conversion factor. 1 foot of water equals 0.433 PSI. So let's use that. 0.433 PSI per foot. So let's plug in the depth. The depth is 15 feet. Multiplied by 0.433 PSI per foot. I can cross cancel. I need to get rid of feet can cross cancel that. I'm left with PSI. This is the unit of measure we're looking for. Let's multiply that out. 15 times 0.433, and that is going to equal 6.495 PSI. The answer, the best answer, is 6.5 PSI W. And just for the record, my lead operator, Brian, is a really great guy. I trust my operators. They're professionals. They understand this is a really great career. I hope they learn something every day, just like I do, which is one of the perks of this industry. But Brian is doing just fine while I'm at home making videos. Question number 8. What is the sulfur dioxide dose in milligrams per liter? What is the dose in milligrams per liter? Well, in this sentence here, we're talking about sulfur dioxide. And the sulfur dioxide is dosed. Let's go ahead and just kind of highlight this. It's dosed at a rate of 0.5 milligrams per liter more than the free residual. Well, we know the free residual, the free chlorine residual, is 2 milligrams per liter. We didn't go over this in previous assignments, so let's see if we can figure it out. What is the sulfur dioxide dose in milligrams per liter equals the free chlorine residual plus the sulfur dioxide let's write this out in a way that we can use it. Our free chlorine residual is 2.0 milligrams per liter. I'm going to add the sulfur dioxide dose of 0.5 milligrams per liter, and that's going to give me, I can do the math right there, but let's just take out the calculator anyway. 2, whoops, let's turn it on. 2 plus 0.5 2.5 milligrams per liter. The answer is B. This question, I don't know if it's still on the exams or one similar to it, but this was on my original, grade 2 exam, I believe. I don't know. It's been a while. You have been assigned to paint the floor of a room which measures out to 675 square feet. 1 gallon of paint covers 50 square feet. How many 5-gallon containers of paint will you need? Well, one of the keys here is to understand that the paint comes in 5-gallon containers. We have to keep that in mind. Each gallon of paint covers 50 square feet. So let's write this out. We have paint by the gallons equals 675 square feet divided by 50 square feet. So the room is 675 square feet. 1 gallon of paint covers 50 square feet. So I need to know how many gallons of paint it's going to take to paint this room. So 675 divided by 50 gives me 13.5 gallons of paint. Well, now I have 13.5 gallons of paint. What am I going to do? I need to know how many 5-gallon buckets it's going to take to paint this room. So let's take, let me just ask a question. How many 5-gallon buckets, containers, whatever, how many of those? Well, I have, it's going to take 13.5 gallons. We're going to divide that by 5-gallon buckets or cans, and I'm writing this down just to make sure it's straight in my head. 13.5 divided by 5-gallon buckets, and that will give me 2.7 5-gallon buckets. 2.7 5-gallon buckets, which is, because I cannot go to the store and buy 2.7 5-gallon buckets. I've got to buy 5-gallon buckets whole. So it's very simple to say 2.7 5-gallon buckets is equal to 3 buckets. The answer is B. I love this question. Again, this is another one that used to be on exams. It's a mind teaser, but it's fun. A single piston reciprocating pump has a 6-inch diameter piston with a 6-inch length of stroke. If it makes 16 discharge strokes per minute, the pumping rate is, and we want it in gallons per minute. So if you know what a piston looks like, you have a piston, some kind of mechanism that pulls it up and down through a cylinder, right? So in this example, we have a single piston reciprocating pump, which has a 6-inch diameter piston with a 6-inch length of stroke, and it makes 16 discharge strokes per minute. What is the pumping rate? Well, let's start with the pumping rate. What is the pumping rate? So pumping rate and that's in GPM, gallons per minute. All right, so I know I have some interesting things here. Gallons. Gallons is a key. I've got 6 inches here, 6 inches here, 16 strokes per minute. I have minute here. Minute is in the unit of measure that I need to calculate for an answer. So I also know that a cylinder is circular, so we're going to start with 0.785, which means I need to find diameter, and this is going to be in feet, because again, I'm seeing gallons. I know that my conversion factor, 7.48 gallons per cubic foot, is going to come into play here. All right. Now the length, this gets it to cubic feet. We want the length in feet. Now, there's 16 discharge strokes per minute, and we want our unit of measure in minutes, so I know that I'm going to add this 16 per minute. I'll just go ahead and put it up here. And that leaves us with 7.48 gallons per cubic foot. Call from work. Somebody left the gate open. So I'm going to finish this and I'm going to go lock the gate. Thanks, Kimberly. Appreciate you calling. All right. 0.785. The diameter. The diameter is 6 inches. Well, 6 inches is not a unit of measure that I can convert to feet or that I can write down. I cannot write 6 inch. It doesn't work in this formula. So I've got to figure out how many feet 6 inches is. I do that by taking 6 inch and dividing that by, because we all know there's 12 inches per foot. So remember, when we write down a unit of measure just by itself, write that like this. It's the same thing as writing down inch over 1. Let's cross cancel. That inch there cross cancels out this inch. We're left with feet. Our answer, and let's do it on the calculator, 6 divided by 12 equals 0.5 feet. All right, now we have that figured out. Diameter, 6 inch diameter piston is 0.5 feet over 1. We have to multiply it by the diameter again, 0.5 feet over 1. The length of the stroke is 6 inches. The length, which is, as we know, 0.5 feet over 1. The number of strokes, (16 per minute), and we'll multiply our 7.48 gallons per cubic foot. Let's cross cancel. We have feet, 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 which cancels out this. We have 1, 1, 1, 16. We're left with gallons and minute. We're looking for gallons. We're looking for minute. Oh, look at that. Now I know that if I multiply this out correctly on my calculator, I'm going to get gallons per minute. Let's try it out. 0.785 times 0.5 times 0.5 times 0.5 times 16 times 7.48, and that's going to give me 11.74 gallons per minute. The answer is B. I gotta go lock a gate, so I'll be back in a few minutes. Question number 11. What is the temperature difference in degrees Fahrenheit between the water source and the processed water in a storage tank? If the temperature of the water source is 12.6 degrees Celsius and the water in the storage tank is 16.3 degrees Celsius. So what is the temperature difference in degrees Fahrenheit? Now with this question, first we have to convert Celsius to Fahrenheit for both temperatures. Once we do that, then we can find the difference. So the formula, remember, is what is the temperature difference in degrees Fahrenheit? So always start off with degrees Fahrenheit. And we're going to take the degrees Celsius, multiply that by 1.8, and add 32. So the temperature is 12.6 degrees Celsius. All right. Get our calculator out. 12.6 times 1.8 equals 22.68. We're going to add 32, and that's going to give us 54.68 degrees Fahrenheit. Now let's do degrees Fahrenheit equals degrees Celsius times 1.8 plus 32. Now we're going to do our 16.3 degrees Celsius times 1.8 plus 32. 16.3 times 1.8 equals 29.34. Add 32, and that equals 61.34 degrees Fahrenheit. Makes sense, huh? 12.6 degrees Celsius equals 54.68 degrees Fahrenheit. 16.3 degrees Celsius equals 61.34. Now let's take those and let's find the difference. 61.34, we're going to minus or subtract 54.68 minus 54.68, 6.66 degrees Fahrenheit. The best answer, 6.7 degrees Fahrenheit, B. Question 12. If the desired dose for chlorine is 2 milligrams per liter, how many pounds of chlorine per day will be needed to treat 2.1 mgd, million gallons per day? How many pounds per day? All right, let's go to our Davidson pie wheel. Feed in pounds per day. Flow in million gallons per day. Dose in milligrams per liter. weight of water is 8.34 pounds per gallon. So the desired dose is 2 milligrams per liter, 2.0. The flow is 2.1 million gallons per day. So all I have to do is multiply 2.1 by 2.0 by 8.34. That's going to give me feed in pounds per day. 2.1 times 2 times 8.34, 35.03 pounds per day. The best answer is B. Question 13. What is the chlorine dosage in milligrams per liter if 4.6 mgd is treated with 55 pounds per day of chlorine? So what is the dosage in milligrams per liter? Milligrams per liter is the same as parts per million. Please keep that in mind. We're back to the feed problem, or the feed equation. Pounds per day. We have flow in mgd, dose, milligrams per liter, the weight of water, 8.34 pounds per gallon. What is the chlorine dosage? That's going to be X. 4.6 mgd, and we have 55 pounds per day of chlorine. Let's see what that gives us. So we're going to multiply 4.6 times 8.34. And that's going to give us 38.36. We'll put the 55 up there. 55 divided by 38.36, and that's going to give us 1.43 milligrams per liter. We'll go ahead and write it right there. 1.43. The best answer is A. This question, we have not covered this in previous assignments, and it's not going to be as difficult as you think. How many pounds per day of liquid alum are used if the flow rate is 12.7 million gallons per day and the dosage is 8.25 milligrams per liter? The purity of the alum is 48%. So the chemical we are using to feed alum into the water, this is usually done on the water side in water treatment, is 48% alum. Now what we've been doing so far with these feed problems is calculating, for example, how many pounds per day of chlorine is necessary to get a certain dose. In this case, we're going to look at the chemical we have available to us, alum, that's mixed with the medium that carries the alum to the treatment process. And this chemical is 48% alum. That's the active ingredient. It's the only ingredient that matters. So how many pounds per day? Pounds per day. Doesn't matter that it's liquid alum. In this case it is. Could be a number of other chemicals, but we're going to start here with our pi. We're going to write feed in pounds per day, flow in mgd, dose milligrams per liter. The weight of water, 8.34 pounds per gallon. Now, let's fill in the missing information so we could make our calculations here. So the flow rate is 12.7 mgd. The dosage is 8.25 milligrams per liter. So we have these three figures we can multiply across to get our feed in pounds per day. Let's do that first. 12.7 times 8.25 times 8.34, and that will give us 873.82 pounds per day. Now, that 873.82 pounds per day, that's not the chemical we're using, that's 48% alum. This is 100% purity. Okay? So how do we get, how much alum are we going to feed, or how much of this medium are we going to feed that is made up of 48% alum? To get the proper amount of chemical? Well, what we're going to do is take the feed. Let's start with this. We're going to take the feed in pounds per day equals 873.82 pounds per day, which is, just do a little bit of this, 100% purity. This is the way I write this so it makes sense to me. I'm going to divide this by 48%. But we need to convert 48% to a decimal. How do we do that? Well, let's take 48%, divide by 100. 48 divided by 100 equals 0.48. So just as I would take $1 and I want 48% of that dollar, it would be 48 cents. 48% of 100 is 48. So 48 cents is written as 0.48. So let's take 873.82 divide by 0.48, and that's going to give us 873.2. Whoop, nope. 873. What is wrong with this finger? 873.82 divided by 0.48, and that's going to give us 1,820.46 pounds per day. Our best answer is C. This is going to be a great question. A 2-foot diameter pipe, 3.2 miles long, was disinfected with chlorine. If 82.9 pounds of chlorine was used, what was the dosage in milligrams per liter? All right, so there's multiple parts to this. And again, we didn't do this in previous videos, but stick with me. We have a 2-foot diameter pipe that's 3.2 miles long. There's a few things that we have to consider. First of all, this is a pipe, right? Laid out horizontally. It's 2 feet in diameter and 3.2 miles long. Well, let's look at our ABC math formula sheet. We're going to go to our conversion factors. And 1 mile, here it is here, 1 mile is equal to 5,280 feet. Now that's important to know because a pipe is a very long cylinder. So we know we're going to be using 0.785. Now, this 2-foot diameter pipe, 3.2 miles long, was disinfected with chlorine. If 82.9 pounds of chlorine were used, what is the dosage in milligrams per liter? So let's start with this. And we're going to use a variation of the feed pie chart. Pounds per day. Now, instead of flow, I'm going to write down, what should I use? Volume. But instead of volume in cubic feet or in gallons, I'm going to use the unit of measure million gallons per day. We could even say million gallons, because we're talking about a volume, not a time period. We want dose in milligrams per liter. The weight of water, 8.34 pounds per gallon. Now that we have that, let me write just a note here. Our known. We got from our conversion table that 1 mile equals 5,280 feet. Okay. So let's fill in some information here. We have 82.9 pounds of chlorine. We'll go ahead and write that right there. We don't have the dose is what we're looking for. The volume in million gallons, and let's just go ahead and put a line through there. The volume in million gallons is what we need to calculate. We're going to use that. We're going to do that using this formula that we're very familiar with. Volume in gallons equals, and this is a cylinder, 0.785 times the diameter in feet multiplied by the diameter in feet, and then we're going to multiply length in feet. Note this unit of measure in feet. This is 3.2 miles long. We need to convert miles to feet. And then, because we're trying to determine the volume, we need 7.48 gallons per cubic foot. Now let's rewrite this equation with all the proper variables. Equals 0.785 times the diameter. The diameter is 2 feet. Multiply that by the diameter again. 2 feet over 1. The chupacabra is probably chasing a moth. He loves moths. Now we're going to multiply it by the length. But the length needs to be in feet. What do? Well, we know we have a pipe that's 3.2 miles long. So I want length in feet equals length 3.2 mile over 1. We're going to multiply that by 5,280 feet per mile. Let's cross cancel. I'm looking for feet. I have mile over 1, foot over mile. I can cross cancel these. I'm left with feet. That's the unit of measure I'm looking for. Get our handy dandy calculator out here, non-scientific. And we're going to multiply 3.2 times 5,280, and that's going to give us 16,896 feet. So let's write that down right here. 16,896 feet over 1. And then we're going to multiply that by 7.48 gallons per cubic foot. It's time to cross cancel. So we have feet, 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 and that cross cancels out cubic feet. We're looking for gallons. We have gallons here. There's no other units of measure. Leaves us with gallons. So I'm going to multiply this across, and that's going to give me the correct answer. Let's do it in a different color. Let's clear that out. 0.785 times 2 times 2 times 16,896 times 7.48. That gives us 396,839.73 gallons. But wait, we're not done yet. We need to convert this to million gallons. How are we going to do that? Well, let's take 396,839.73 gallons, divide that by 1 million. Here it is on my calculator. I'm going to hit divide by 1 million, and that gives me 0.39, and I could go 6839 blah blah blah. So let's just go ahead and convert that to 0.4 million gallons. We'll just round it up. I can round up that 3 to a 4 and make this a 0. That's what I've done. All right, so let's write that in our volume, 0.4. Well, now I have the feed, 82.9 pounds per day, the volume, 0.4 million gallons. I'm solving for X, which is the dose, and I have the weight of water, 8.34 pounds per gallon. Let's multiply this across. That's going to be 0.4 times 8.34. That equals, so up here we have 82.9 divided by 3.34. Let's call it 3.34. Let's do the math. 82.9 divided by 3.34, that equals 24.8 milligrams per liter. The best answer is D. It seems complicated. That's a lot of math to do to get this little answer. I understand. It seems like it's overwhelming. It seems a little intimidating. But all the problem is right there. All the information you need is right there. The key is units of measure. I've emphasized this so many times, and that's why I use this process to cross-cancel, to break it down, to make sure that I'm getting everything accounted for in the equation to get the unit of measure I'm looking for. It's just repetition and understanding what is your goal, what information do you need to complete the question. Okay, back to something simple. Convert 350 degrees Celsius to degrees Fahrenheit. We are looking for degrees Fahrenheit. So let's start off with degrees Fahrenheit equals degrees Celsius multiplied by 1.8 plus 32. So we'll write 350 degrees Celsius times 1.8 plus 32 times 1.8 equals 630 plus 32. That gives me 662 degrees Fahrenheit. The best answer is D. Question 17. Which of the following is the same as parts per million? Oh, this is such a great question. Parts per million. Well, we know that ppm stands for parts per million. We know that milligrams per liter is the same as parts per million. What about liters? Liters per mgd. Liters and gallons don't add up. We know it's not A. Water weighs 8.34 pounds per gallon. We know this. But 1 million pounds of water does not match up. 8.34 pounds would be 8,340,000 pounds. So we know it's not C or B, excuse me. Well, 1 pound to 1 million pounds, that looks like the correct answer. 1 pound to 1 million pounds is 1 part per million. And just to double check ourselves, a milliliter per gallon? No. We're going to go ahead and just X that out. The answer is C. Okay, question 18. What is the area of a circular clarifier with a diameter of 22 feet and a depth of 12 feet? What is the area? What is the area of a circular clarifier? Well, this is a circle, so we are going to write our formula. Area is expressed in square feet. Because this is circular, we're going to go with 0.785 multiplied by the diameter in feet multiplied by the diameter in feet again. Have a foot here, square feet. We know this is correct. We also know that the depth has no meaning in this question. This is extra information. Don't need it. So let's go ahead and rewrite the equation. diameter is 22 feet. Multiplied by the diameter again. We have foot here, we add those together, we get square feet. 0.785 times 22 times 22. The answer is 379.94 square feet. The best choice is 379. The answer is C. All right, question 19. If a run of pipe is 828 feet and it drops 13 feet in elevation, the rise of the run is... This is another question. We did not go over this in the in the previous lessons, but this is not difficult. So the formula for this is, and you've probably heard this before, rise over run. It's that simple. Rise over run. So let's take the information and drop it in there. The rise of the run is, so let's write it down like this. The rise equals rise. The run of pipe is 820 feet. It drops. Now in this case, rise and drop. I often hear contractors calling it the drop, but and you can use that interchangeably as far as I know. Whenever I speak to people about this, everybody understands what we're talking about, and that's reality, that's in the field. So it drops 13 feet. We're going to divide that by the run, which is 828 feet over 1. Let's cross cancel. I'm going to get rid of that foot, get rid of that foot. We're left with 1, or no unit of measure. 13 divided by 828 equals 0.01. Let me double check that. 13 divided by 828 equals, look at that, 0.0157. The correct answer is C. Now, just a quick note. When we're laying a gravity sewer, for instance, we want gravity to do all the work of taking the water from where it enters the pipe to the point it leaves the pipe. Gravity is the least expensive form of energy. If I can lay a pipe 20 miles long that would take the water from its source to the destination and never have to use a pump, which requires electricity, which requires maintenance, which requires man hours, gets very, very, very costly. If I could lay that length of pipe and only use gravity, it makes it much more affordable for the utility. So to get the proper flow, now we don't want the pipe to be angled in such a way or sloped in such a way that the water runs so fast through that pipe that it wears out the inside of the pipe. We don't want the water, we don't want to lay that pipe at a slope that is so shallow, almost flat, that the water just doesn't want to run. We want to angle it just right. And this is how those calculations are made by engineers and the man in the field that lays the pipe. They know that a slope of 0.0157 is going to allow the water to flow at a certain velocity by gravity. There'll be more on that later in other videos, another video series. We're already on question 20. 2 columns of water are filled completely to a height of 88 feet. Column A is 5 inches in diameter. Column B is 5 feet in diameter. What will the pressure gauges located at the bottom of each column read? Now, we covered this in a previous lesson. It doesn't matter the diameter. The diameter can be 5 feet in diameter for one column, 50 feet in diameter for another column. It doesn't matter what the width is or the diameter. What matters is the level of the water measured down to the bottom. So we want PSI. PSI equals depth in feet multiplied by our conversion factor, 0.433 PSI per foot. So for every foot of water is 0.433 PSI. That's our conversion factor, that's our fact. So let's rewrite this. Depth, and again, 2 columns of water filled completely to a height of 88 feet. 88 feet over 1 multiplied by 0.433 PSI per foot. Let's cross cancel. We're looking for PSI. We want to get rid of this foot and that foot. Leaves us with PSI. That's the unit of measure we're looking for. 88 feet times 0.433, and that's going to give us 38.1 PSI. What's the closest answer? The answer is D. Column A, 5 inches. Column B, 5 feet. It's the same pressure on both sides. We're back. Let's go to question 21. What is the volume of a sedimentation basin 75 feet in diameter and 14 feet in depth? What is the volume? And the volume is going to be in gallons. So to get volume, in gallons, this has a diameter, so it's circular. We're going to start with 0.785. Multiply that by the diameter in feet, by the diameter in feet again. Then we want the depth in feet, and we're going to use our conversion factor, 7.48 gallons per cubic foot. So let's use this formula to rewrite our equation. 0.785 times the diameter the basin is 75 feet in diameter. The depth, 14 feet. Gallons per cubic foot. Now, let's cross cancel this out. Feet, 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 foot cubed. These are the gallons. That's the unit of measure we're looking for. Multiply this out. 0.785 times 75 times 75 times 14 times 7.48. We're getting 462,404.25 feet. The correct answer is D, 462,400 gallons. Question 22. 1,487 pounds per day of BOD enters the system. What is the population equivalent? BOD stands for biological oxygen demand. So in layman's terms, BOD is number one, anything that's organic that breaks down because bacteria is consuming it. Now the bacteria need a certain amount of dissolved oxygen in the water before they feel they can eat. So the bacteria at the wastewater plant, you have to understand this, that all the wastes, all the solids that, or the BOD that enters a plant, like an aeration basin where we house the bacteria, it's consumed by bacteria. So as a wastewater treatment plant operator, one of our biggest jobs is to maintain an environment in the aeration basin that will allow the bacteria to not even think about if they have enough oxygen. They need plenty of oxygen so they can just naturally do what we want them to do, and that is to eat the solids that come into the aeration basin. They consume the solids, they use it to grow new cells, to divide, to multiply, to live their life. And as they consume that BOD or those solids, they digest it, break it down, and reduce it. It's a process of reduction. Reduce it to something smaller. Bacteria come in behind them and consume that matter. It gets consumed again and again and again, and that's how we remove the solids out of the water to treat the water. Now, when we talk about population equivalent, and in this example, we have a wastewater plant that has 1,487 pounds per day of BOD, probably on an average, that enters the system that comes into the plant. So it's probably not a very big plant, but let's talk about, so when we look in our ABC formula conversion table, we'll go to our conversion factors. And we'll find population equivalent organic. And our conversion factor is 0.17 pounds BOD per person per day. What does that mean? Well, that very simply means, on average, each and every one of us will flush 0.17 pounds per day of solids. We poop, and on average it's 0.17 pounds worth of poop. So everything I ate yesterday, everything I consumed has been digested, and this morning I pooped it, flushed the toilet, let it go into the collection system, job security. So this is an important conversion factor to understand in the wastewater treatment process, especially as a wastewater treatment plant operator. This is the average 0.17 pounds per day of BOD. So we want to know how many people contribute 1,487 pounds per day of BOD to the system. So people. And we're going to do some division here. 1,487 pounds per day. And we're going to divide that by the conversion factor, 0.17 pounds VOD per person per day. Okay. That gives us 8,747.0506 people. The best answer is C, 8,747. Question 23. What is the capacity in a basin which measures 40 feet long, 15 feet wide, and 15 feet deep? Capacity. What is the capacity? It looks like this answer is going to be in gallons. Just write it right there. So we're looking for, remember, capacity equals volume. So we want the volume in gallons. This is a rectangular basin. I know that because it has a length, a width, and a depth. So we want the length in feet, the width in feet, and the depth in feet. Now, the unit of measure is in gallons, so we know that once we get the volume in 3 cubic feet, we can use our conversion factor, 7.48 gallons per cubic foot, to convert it to gallons. So we'll write that right here, gallons per cubic foot. One, two, three. Cancel out the cubic feet. We're left with gallons. The length is 40 feet. The width is 15 feet, and the depth and then we multiply by our conversion factor, 7.48 gallons per cubic foot. Let's make that a 3. All right, cross cancel. 1, 2, 3. Left with gallons. That's our unit of measure. Let's do some multiplication here. And that equals 67,320 gallons. The correct answer is B. Question 24. A pressure gauge on a cylindrical tank, 32 feet in diameter, 22 feet in height, reads 7.65 psi. What is the water depth inside the tank? What is the water depth inside the tank? Well, we want the depth in feet. We know that the pressure gauge reads 7.65 psi. And we'll do PSI over 1. And we know our conversion factor, 0.433 PSI per foot. So, and that's written as 0.433 PSI over foot. Now, where's the PSI? Our unit of measure that we're looking for is feet. We want to keep feet. We want to get rid of PSI. Here it's over the division line. Over here it's over the division line. So that means we need to divide 0.433 PSI per foot. That allows me to cross cancel out the PSI. Leaves us with feet. That's the conversion factor. That's the unit of measure we're looking for. Divided by 0.433. That's going to give me 17.67 feet. The correct answer is B. That's the closest answer. Question 25. How much water in mg, million gallons, can a basin measuring 120 feet in diameter and 18 feet in depth hold? So we have how much water in mg, million gallons. So let's start by volume in gallons equals, and this is a circular basin, 0.785 times the diameter in feet, the diameter in feet again, times the depth in feet. We're going to multiply that by 7.48 gallons per cubic foot. 1, 2, 3, this, gallons. Gallons is what we're looking for. I like to just double check myself every step of the way. The diameter is basin measuring 120 feet in diameter. 120 feet over 1. Diameter 120 feet over 1. The depth, and 18 feet in depth. 18 feet over 1. Multiply that by 7.48 gallons per cubic foot. Let's cross cancel. Foot, 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 cubic feet, left with gallons. That's the unit of measure I'm looking for. So 0.785 times 120 times 18 times 7.48, and that's going to give us 1,521,970.56, and that is in gallons, but we are looking for million gallons. So let's do million gallons equals 1,521,970.56. Divide that by 1 million, and that gives us, here's my number, here's my answer, divided by 1 million, and that gives us 1.52 million gallons. The correct answer is C. Question 26. Calculate the pressure in pounds per square inch at the bottom of a tank if the water level is 33.11 feet in depth. what is the pressure in PSI? PSI equals, and remember our unit of measure is 0.433 PSI per foot. So we want the depth of the water in feet. Foot is going to be expressed as feet over 1. Over here, which that'll be above the division line. On our conversion factor, it's below the division line, so we're going to multiply 0.433 PSI per foot. And do you see why I did that? We want to eliminate the feet and be left only with PSI. So let's rewrite the formula, plugging in this information. Depth is 33.11 feet. So I can cross cancel out feet. I have PSI. That's the unit of measure I'm looking for. Let's multiply this out. 33.11 multiplied by 0.433 equals 14.34 PSI. The correct answer is A. I have time for one more and then I need to get to work. It's almost 5:30. Convert 34 cubic feet per second to gallons per minute. I need GPMs. So I like to rewrite this. And by the way, CFS equals cubic feet per second. 34 cubic feet per second to gallons per minute. So I want to convert 34 cubic feet per second to gallons per minute. So let's think about this for a second. I'm seeing gallons, I'm seeing cubic feet. Look at my conversion factor, 7.48 gallons per cubic foot. I see seconds, but I need to convert it over to minutes. I know there are 60 seconds per minute. So let's start with that. We'll write it in blue here. Gallons per minute equals 34 cubic feet per second. Now, there's 60 seconds in a minute. And in this 34 cubic feet per second, second is below the division line. There are 60 seconds in a minute. Seconds in 60 seconds per minute is above the division line. So I know I need to multiply. 60 seconds per minute. You see what I'm saying there? Seconds is below the division line. Over here, it's above the division line. I'll be able to cross cancel those out. Now I need to use 7.48 gallons per cubic foot. I have cubic foot above the division line here. In my conversion factor, it's below the division line, which means I multiply. Boy, it's a good thing I'm going to work. I'm having a difficult time writing this morning. So I can remove or cross cancel the cubic feet out. I can cross cancel out the seconds, and I'm left with gallons per minute, which is the unit of measure I'm looking for. Let's do a little multiplication. 34 times 60 times 7.48. And that gives me 15,000 259.2 gallons per minute. The correct answer is D. Let's continue. We're at question 28. Calculate the volume of a trench, 363 feet in length, 3.5 feet in width, and 6 feet in depth. We've done a bunch of these. We can get this done. Calculate the volume of a trench. That's what we're trying to do. Pay attention. Read these questions a couple of times. Make sure you understand what they're asking you. Calculate the volume of the trench. So we are going to, looks like cubic feet. So volume, cubic feet equals the length in feet multiplied by the width in feet multiplied by the depth in feet. Now's a good time to mention that operators should be able to write legibly. Should be able to, we do a lot of writing in record keeping. Record keeping is super important in this industry. I know lately there's been in the last several years, we're moving towards using pads like iPads to record information and maintain the records, but there's still a lot of people out there handwriting on their bench sheets, on their maintenance sheets, things like that. And whenever you have to do it, please write legibly. It'll help out at someday. It helps out your operators in the future when they're looking at historical records. All around, you want to write as legibly as possible. The length. The volume of a trench, 360 feet in length. The width. .5 feet over 1. The depth, 6 feet over 1. Real quick, we're going for 1, 2, 3. We have 3 feet here per cubic feet. Let's make sure we've got that right. We have foot, foot, foot. That's the unit of measure we're looking for. Run the calculator. 363 feet times 3.5 feet times 6 feet. 7,623. 7,623 cubic feet. The answer is C. Question 29. What is the volume in cubic yards of the trench described in question 28? Boy, what a great question. What is the volume in cubic yards? Well, there's certain things that we know. For instance, we know that 3 feet equals 1 yard. We know that 3 feet multiplied by 3 feet multiplied by 3 feet equals 27 feet cubed. So we know that 27 feet cubed equals 1 cubic yard. All right, because 3 feet equals 1 yard, we have 1 yard, 1 yard, 1 yard. That's 3. 1 cubic yard. We also know that in question 28, the volume is 7,623 cubic feet. Remember the previous question, 28, we calculated the volume in cubic feet, 7,623. So what do we do with all these known, with all this information? We want to calculate the volume in cubic yards. That's what it's asking us for. Equals, we know that the volume in question 28 is 7,623 cubic feet. We're going to divide that by 27 cubic feet per cubic yard. So we know that cubic foot written in this form, in this unit of measure, is cubic feet over 1. And that allows us to cross cancel. Cubic foot is over the division line here, it's over the division line here. So I can cancel these out. I'm left with cubic yard. That's the unit of measure I'm looking for. So let's calculate this out. 7,623 divided by 27 gives us 282.33 cubic yards. The correct answer, the closest answer, the best answer is D. Question number 30. A wastewater treatment plant with a 0.5 mgd flow has an effluent chlorine residual of 3 milligrams per liter. Apply sulfur dioxide at a dose rate equal to the chlorine residual. Determine the sulfonator feed rate in pounds of sulfur dioxide per day. Pounds per day. We love these. Okay. So we will start with our pie that has no edge. We've done a bunch of these. This will be easy. Feed in pounds per day. Flow in million gallons per day. Our dose in milligrams per liter, and our unit of measure for the weight of water is 8.34 pounds per gallon. Let's fill in the gaps. Let's fill in the information that we know. Well, the flow is 0.5 million gallons per day, MGD. Has an effluent chlorine residual of 3 milligrams per liter. Apply sulfur dioxide at a dose rate equal to the chlorine residual, 3 milligrams per liter. Okay. 3. We could also write it 3.0. Whatever you fancy. That sounded weird. 0.5 times 3 times 8.34, and that's going to give us 12.51 pounds per day. The answer is A. Okay. Question number 31. The effluent from a wastewater treatment plant must be dechlorinated before discharge. At the sulfonator, the chlorine residual is measured at 1.7 parts per million, with a 2.8 million gallon per day flow, and a sulfur dioxide residual of 0.2 milligrams per liter is desired. Calculate the feed in pounds per day of sulfur dioxide necessary to achieve the desired residual. So we want feed in pounds per day to get the desired residual. So we know that the chlorine residual is measured at 1.7 parts per million. So we'll write chlorine residual equals 1.7 milligrams per liter. We want residuals measured with a 2.0 and a sulfur dioxide residual of 0.2 milligrams per liter is desired. So we want so that means if we add 1.7 plus 0.2, the dose will equal 1.9 milligrams per liter. Wrote down our knowns and included the math to help us make these calculations. So let's draw our pie. This is feed in pounds per day. Flow in million gallons per day. Our dose in milligrams per liter. Our conversion factor of the weight of water, 8.34 pounds per gallon. Now let's enter the information that we have, that we know. Let's start with the effluent from wastewater to be chlorinated versus sulfur. 1.7 parts with a 2.8 mgd. And we've calculated the dose to be 1.9 milligrams per liter. We have some calculations to make here. 2.8 times 1.9 times 8.34, that gives us 44.37 pounds per day. The best answer is D. Question 32. Water is flowing through a channel 4 feet wide and 1.5 feet deep. If the flow is 10.5 cubic feet per second, what is the velocity of the water? What is the velocity? And by the looks of it, we want to know what the velocity is in feet per second. Well, let's look at our ABC formula conversion table, our math formula sheet. And we're looking for, we've already done this, velocity in feet per second equals the flow rate in cubic feet per second divided by the area in square feet. So let's write that down. Equals the flow rate in cubic feet per second divided by the area in square feet. So let's rewrite this formula. Filling in this information, the flow rate is 10.5 cubic feet per second. The area is we're going to multiply the width, which is 4 feet over 1 times the depth, which is 1.5 feet over 1. Four times 1.5 equals. So let's rewrite that. Let's rewrite that. Flow rate 10.5 cubic feet per second. We're going to divide that by what now is the area, and that is 6 square feet over 1. Let's cross cancel. We have cubic feet here, we have square feet here. We can cross cancel this out, and we are left with feet over second, which is the unit of measure we want. Let's do the math. 10.5 divided by 6, and that equals to 1.75 feet per second. Does that make sense? Is that the correct answer? I would say the correct answer is A, 1.8 feet per second. The closest answer, the best answer. All right. Question 33, the final question. A person on average contributes 0.17 pounds of BOD per day. A wastewater treatment plant serving a town with a population of 26,000 people would expect an organic load of, what's the organic load? That's what we want to know. What is the organic load? And that will be measured in pounds BOD per day. So we know that the population is 26,000 people. And we know that each person contributes, let's go ahead and write out the formula here, 0.17 pounds BOD per day. A person on average contributes 0.17 pounds BOD per day. 0.17 pounds BOD per day. We know the population is 26,000 people. I'm multiplying it because it's per person. This unit of or this conversion factor is in per person. This is the entire population. 26,000 multiplied by 0.17, and that's going to give me 4,420 pounds BOD per day. The correct answer is D. I appreciate you following along with me. Please like my videos. Please watch them all. Watch them start to end. Like them. Please subscribe to my channel. I invite you to make comments. Tell me I'm boring. Tell me you hate my voice. Tell me my techniques don't work. Or tell me how they work for you. Tell me that even though I might be boring and droll, it helps you understand how to break down the math questions better. In my experience, in all the years I've been training operators, the operators who go in to take their certification exams, if they can get 75% of the math questions correctly, they will pass that exam. And many operators who are intimidated by the math, which is most of them, who don't understand the math, unless they are ready, unless they've studied for their certification exam, they simply don't pass. I hope this series has helped you. Please go to the link on my YouTube channel. It'll take you to my website. You can download all the math assignments in this series for a small fee. It helps me financially. And I think I've priced it so very fairly because I really want to help people. That's one of the reasons I do this. Thanks for being here with me.